Okay, we'll go ahead and get started. First of all, this is COTS-Based RF for SatCom and Telemetry. Everybody here for that session? I think originally there was a counter UAS session in this room, so make sure everybody's not looking for that one, but for this one. Okay, my name is MacCoy. I'm a technical marketer on the aerospace and defense government team, focusing on RF applications, particularly in validation for communications, navigation, and surveillance. And so I'm going to talk to you a little bit today about some of the COTS-based approaches we've taken towards system validation for SatCom. Just a quick show of hands, who has had a chance to see our demo down on the floor for channel emulation? Okay, great. I'm going to talk about that a little bit today, and I'm going to encourage you after the session to go down and check that out. It's in the ADG area of the Expo Lounge when you first walk in on the far left. But, so, based on, wrong direction. So we're going to talk a little bit today about just some overall aspects of the things we can test and evaluate for point-to-point links, particularly as it pertains to SatCom, but also for air-to-ground, air-to-air, ground-to-air sort of communication. We'll talk about typical testing methodologies and what has been done historically. And then we'll talk about the NI COTS-based approach and some of the advantages of using that modularity. So, real quick, just kind of an overview. If you were in any of our sessions yesterday, the spectrum is congested, and so there's a lot of things that can be interfering with different signals, either passively or actively. So when you're talking about these types of links, they're usually not just existing in isolation. There's other things going on in the RF space along with those, and so how do we model those? How do we compensate for those? How do we ensure that our systems are robust enough to handle those sorts of situations? So when you talk about like a ground-to-air link, for example, there's going to be atmospheric interference. There's going to be passive and active signals interfering. There's going to be some multi-path propagation. All these things are going to interfere with your signal. So you want to have a robust way of making sure that you're addressing those situations. In ground to space, you have large delays. You have Doppler effects that are extreme based on the orbital velocities. You have still atmospheric conditions. You might have threats either airborne or on the ground that are trying to interfere with that, or even spacebound threats that are actively interfering with that signal. And then in a ground to air or air to air, you have I already did that one. Air to space is another one we're looking at, where you have Doppler on both the send and the receive side of that, and you have some of these hypersonic rates might have extreme Doppler shifts as they're maneuvering something. So not just the Doppler itself, but the rate at which that Doppler is changing is something we have to be able to compensate for. And then in space itself, there's a whole bunch of host of effects, whether it's radiation from electromagnetic radiation from the sun, or you might have the Van Allen belts, or all sorts of magnetic effects from the Earth itself. You have other satellites. You have long distances that you might have to model if you're talking about a cislunar or interplanetary mission. So there's lots of things that happen when you're in these different environments that you can't necessarily just easily replicate in a lab. And so some of the challenges is how do you do that at an achievable scale? As we're seeing these systems scale up, you're seeing these constellations that have to have the ability to replicate this validation across multiple systems. You can't just build a monolith and let that work for you over a program that's going to take 5, 10, 15 years to develop. These are growing fast, requirements are changing fast, and you have to scale them at an increasingly high rate. The arrows on this are backwards. So typically there's basically four kind of domains that you would have to look at for doing this kind of EGSE testing for electronic ground support equipment. You'd look at RF generation analysis for your parametric test to make sure that your components in your system were working properly. You would want to be able to do some system emulation to make sure you had an endpoint that could match, and a lot of times that would be handled with some sort of golden dot or a system that was standing in for the receiver or transmitter of your system. Environment emulation, that's what we kind of just talked about with. There's a lot of off-the-shelf link and terminal emulators. And they have their own pros and cons. And then you'd have some sort of digital interfacing with avionics and those sorts of things as well. And so typically you have a big rack and stack approach where each of those things has its own unique device, a VNA, a VSA, SIGGEN, spectrum analyzer, IQ data generation, some sort of recording, all these different instruments that would be needed for doing all this long kind of this integrated testing that requires lots of instruments. And racking and stacking all those you might be the easy approach at first because we have instruments that are dedicated for that purpose, but you quickly run into complexity in getting those instruments to talk to each other. You might end up being, if you want to implement custom IP, you have a difficult time of getting that IP onto that because it may be locked by the manufacturer, and then you have to get NDAs in place to modify that. And you end up with a lot of redundancy too. Like you might have a spec end to take one measurement, and then you need a VNA to take another measurement, and then you end up, there's actually a lot of overlap between those measurements where if you had a one set of hardware to do both those measurements would be more efficient. And so the NI approach is to make all of that modular. And so I'm going to talk a little bit now about that. Before I go any further though, everybody in here familiar with PXI, or do we need a little bit of a crash course? One moment. All right. So I'm going to talk about the NI approach. It's based on PXI. If you're not familiar with PXI, come and see me afterwards. We'll get you up to speed on that. But I'm going to assume that we all kind of understand the basics of PXI and the platform approach of modularity, common timing, and synchronization across instruments in that basic approach. And so what we have is defined as a modular software-defined eGSE where we can run the RF using our VST, which gives us the spectrum analyzer signal generator and the FPGA to log streaming of that data. And then we use our coprocessors to add impairments to that data or to emulate different parts of the tool chain. So what I'm showing here is our channel emulation system software. We'll talk about that more in a little bit. But what that allows us to do is emulate the actual channel, add impairments to that channel like Doppler or fading or other impairments that you might see in the signal chain. And then also we can use a VST to do signal generation analysis. So in line, while you're doing this emulation, you can also pull RFMX and you can look at things like adjacent channel power or a basic spec end if you want to troubleshoot something. And so, like I said, the vector signal transceiver is the heart of all this. That's what allows us to do both the generation and the analysis, and then the FPGA backend allows that streaming of that data. Just quick show of hands, who's used VSTs before? All right, cool. Who has considered VSTs and gone other directions? All right, we'll talk. But it's a very good tool. We're on a third generation now, so there's a lot of legacy built into this. We've been iterative on our approach to it, but it is also, at this point in time, best in class as far as wideband capabilities and also the ability to achieve narrowband measurements. It's got up to 4 gigahertz of instantaneous bandwidth, 26.5 gigahertz of range, but we can extend that up to 54 gigahertz, so that gets us into a lot of these SatCom applications. And then again, using that coprocessor, on top of that, we're able to add in impairments or other real-time real-time emulation of different parts of the signal chain. So these two instruments, the VST and the coprocessor, are the heart of not just the SatCom sort of application, but all of our advanced complex systems for our radar, EMSO, and communication solutions is this basic architecture of VST and coprocessor, giving us that ability to do signal generation, signal analysis, and real-time streaming. So I highlighted all these already, but I'll just flash it there in case anybody wants to take a picture. And then, so what we're looking at with this is the actual tool chain for a use case of using chess for basic digital channel emulation, where we're using the 7893 you see there to implement we're adding the Doppler delay and attenuation onto the baseband signal, and then sending that to the VST to generate an RF signal from the impaired baseband signal. I think, okay, yeah. So what we're looking at with the data link test framework is another solution that we have in our toolkit. This allows us to do things like modem emulation. So now we can emulate not just a channel, but we can also emulate an endpoint. So if you have a receiver and you need a transmitter, you have that. Or if you have a transmitter and need a receiver, you have that. Or if you have a duplex system, you can emulate the modem on both sides. So what this allows us to do, we have a partner that has some CCSDS modulation, which will have examples for all sorts of modulation schemes. We can stream the bandwidth at up to 2.5 gigahertz samples per second per direction. This works with all of our vectors signal well, not all, but the 5841, the 5842, and also a variety of our coprocessors. So this gives us, now we have channel emulation, we have endpoint emulation. That's how we get end-to-end telemetry validation. We're able to combine these things together. So this is what that looks like, where we have a modulated signal out of one coprocessor going through our emulation coprocessor, adding those impairments to the baseband signal, and then sending it to our VST to transmit. And then if you had your DUT on the one side, you would be able to see how that was received, and then you could send that back. And then you could see how that whole signal chain from end to end, as the title of the session said, we can emulate that entire end-to-end using just COTS hardware and commercial software that we've developed. And then if we needed extra bandwidth, so that would be by doing it in this configuration, you're basically for a 2 gigahertz instrument, you get 1 gigahertz of bandwidth in each direction. 2 divided by 2 is 1, so that's how that works out. But if you needed that full bandwidth, you could do 2 gigahertz in a single direction, and then turn it around and do it in the other direction. But you just want to be able to do that in real time in both directions without using an extra coprocessor. If you had additional coprocessors, this coprocessor will limit the actual bandwidth. So if you wanted to use the 4 gigahertz VST and do 2 gigahertz in each direction, you could do that with additional coprocessors. So now we're starting to get to the advantage of the modularity. Not every customer needs 4 gigahertz of bandwidth, so you get a VST that has just a 2 gigahertz. We even have VSTs that are good. The same VST, we can get 500 megahertz, 1 gigahertz, 2 gigahertz, 4 gigahertz bandwidths. You get the frequency ranges you need, so you get into the modularity advantages there, where you can right size your system for your use case, and then you can easily upgrade that system for future use cases. So today, you just want to do proof of concept. You're going to do half a gig at 8 gigahertz. You can get a VST that does that right now, and then you get into an actual mission deployment where you have to be at a higher frequency band and more gigahertz. You can send that VST in, and we can recalibrate it and send it back to you for a nominal fee, or you can add additional VST capabilities or additional coprocessor capabilities to be able to increase your tools without actually getting a whole new system. So now the modularity starts to show its advantages as well. And so there's other things we can also use. We can bolt on other types of IP. For example, we can bolt on an EW emitter so that we can emulate some of those harsh EW environments where we're not just emulating the channel, we're emulating the environment that channel is going through with an active or passive jamming, or just maybe there's a lot of Bluetooth in the area. You want to see what that does to your receiver. You want to do you want to add a recorder onto that, so you want to be able to record and play back this. Either you want to capture a signal, and you just want to record that signal back and forth, so you have a real signal you're using for your validation rather than just something you've generated in your lab. You can use our RPS system to capture that and then play it back, or you want to capture that so you can do offline advanced analysis and see certain things. You can do that, so you can do asynchronous analysis, not just looking at the streaming in real time. So a lot of capabilities, and then the advantage of the modularity is that all these work together, and you can kind of a la carte pick what you need to build out a system you need. So it is flexible, like Luke said this morning, it's a flexible system, but it's robust because it's all supported by NI technology that we've proven out and we know how to support. So you're not just having to go do it yourself, we're not just giving you an FPGA and a signal generator and signal analyzers and saying, go figure it out. We're giving you the tools you need to build your system so you can get quicker to getting the tests you need without having to get a custom system that might come from a provider that would build a whole system for you, but then they've locked that IP out, so you can't go ahead and say, actually, I need this type of waveform, I need this type of scenario. And I want to also clarify is, while we're providing emulation of the environment, we are not providing scenario simulation. So this allows us to be agnostic to what the scenario is. We provide plugins for things like ANSYS SDK and other scenario generators that can provide those things like, as a satellite passes over a ground station, here are the Doppler effects that it would see. We can feed those in real time into the emulator so that you can use your simulated data to generate an emulated environment. And that's the example we have downstairs, where we're showing ANSYS SDK generating a simulated scenario, feeding those parameters through a Jupyter link into the channel emulation, and using those parameters to actually modify the signal that is being applied to the IQ stream. So that's kind of what I'm showing here as well. It's like a typical test track would have probably all of these and more. You have an IQ data recorder, mission receiver, VNA, spec-in. You take all that and you can squeeze all that into just a few slots of a PXI chassis. Between the VST, the coprocessor, and if you'd like a VNA to check S parameters before, if you're getting a weird signal or something, you want to make sure single slot VNA just to help you with your setup. Coprocessor to do all of the system emulation, channel emulation, and then a VST to do the actual RF. You throw RFMX on there so you can do your spec-in and your typical parametric measurements. You have a full reconfigurable emulation test kit with data link emulation, channel emulation, and parametric tests all in 8 slots, 10 slots? So that's for a single channel. And then you can also scale that up to a single channel. You can do a 4-channel system with one of our system on-demand racks, or we can even do 16 channels. And even though these are in different chassis, they're still phase and time aligned. So we can make these with sub-nanosecond time alignment and phase coherency. All our signals maintain that same phase coherency across chassis and across multiple channels. So that allows you to do multiple channels for whether it's a comm system that has multiple is channelized like that, or you have multiple DUTs you want to test at the same time in some sort of advanced testing scenario. And so just going back to where we started, where you have kind of all those kind of 4 requirements. We don't do the 4th one, we don't do avionics. So you would interface with the other half of our team that does the avionics testing to figure out how to do that. We have plugins so that you can move data, you can take this data and move it into the avionics buses to see how that works. But our focus is on all the RF side of that. So it's the RF generation and analysis, the system emulation, and the environment emulation, all being done again on these 9 or 10 slots using the VST, maybe a VNA, and a coprocessor. We can do channel emulation. We have third-party links, so we partnered with engineers to do some of that CCSDS modem emulation. We know we've worked with ANSYS to do the simulation, but there's other ones that also, if you have your custom one that you like, that you want to use, and that's one of the advantages of the flexibility of using this COTS-based system is maybe you start using ANSYS and you just don't like it, or you have a customer that's got a different scenario, then they have their own custom IP that they want you to run. You don't have to go back to the manufacturer, you don't have to come back to us, you just create your new plugins and you plug it right into those data hooks for your new scenario, and you're up and running in a couple hours. So what this does is provide a flexible platform for you to do end-to-end telemetry validation, whether it's transmit, receive, or duplex. So again, all these systems are evolving more and more rapidly. They're becoming more and more complex. The environment is becoming more and more complex. All this requires us to continue to be flexible so that we can adapt to these new environments. Using our COTS-Based approach, our modular platform, our modular tools, and our IP that has been proven out, this allows you that flexibility to continue to evolve. We'll continue to evolve so that you have the latest and greatest abilities to, as we add more frequency range, more bandwidth, more IP, more, all these things that we can add into this. It gives you a flexible platform to continue to build on. And we can partner with you to continue building these systems that are scalable, flexible, and robust. With that, are there any questions? If not, I'll start calling on people. Who here works with SatCom applications? All right, who here just is curious about channel emulation for other applications like 5G or wireless or any of those? All right, we are looking, the version that we've built here is targeting for these distance communication like air-to-air, air-to-ground, but there are some features in our next iteration that'll probably be 12 to 18 months out, or that will be targeting some of those 5G and wireless types of applications. So talk to your Cebu friends for that. If there's no questions, we can all take a field trip and go look at the demo downstairs if we want.
I've seen it.
All right, yeah, let's go do that. I'll hang out here in case anybody wants to come up, but there's people down there giving the demo. And then if there are any questions and you think of them later, just feel free to contact me. There's a whole bunch of information at ni.com/chess, easy to remember. Scan the QR code, a whole bunch of information there on where we are today and where we're going in the future with this. Thanks for your time.
Thanks for joining me. Today, we're going to demonstrate what we call our channel emulation system software. I have a hardware setup here that consists of 2 coprocessors and a VST. So what I'm showing now is our ability to generate a modulated signal in the baseband, send it through the VST as a transceiver and back again for modulation and demodulation. On my screen, I'm showing you a basic QPSK signal being modulated, sent and received. I can easily change that to other modulation schemes, so something like a complex 64 APSK, and we can see that constellation update. But I'm not just sending it back and forth through the VST. I'm also sending it through a second coprocessor and doing what we call channel emulation. What I'm doing with channel emulation is I'm adding impairments in real time to that baseband data before sending it to the VST. What this enables us to do is emulate real-world environments where I have path losses and interference for things like frequency shifts, Doppler shifts, and all sorts of real-world things that happen with satellite and other communications. So what I'm showing here on my top screen is the unimpaired signal being sent to my VST. Also, on the bottom screen is what would be impaired. Right now, it's not showing any impairments. But let's see what happens if we add some frequency shift to this signal. Let's say something like 440 kilohertz of frequency shift. You can see on my demodulated signal that I'm starting to lose the ability to resolve those signals. I'm getting some fuzziness around the IQ data. And at higher different modulation schemes, that becomes even more of an issue. It just still that same fuzziness. So that is with adding a frequency shift. We can also do things like, if I take out my frequency shift, I can also do things like adding a fading profile. So for this demo, I've set up a simple fading profile that I will import. Once I stop my channel emulator, I'll import it. I'll add some nominal spread here. And run. now I can see a different type of spread on my demodulated data. I'm seeing these clusters resolve around my target vectors, and we see how that impairment affects our ability to demodulate the signal by my receiver. Again, at a different modulation scheme, this becomes even more of an issue. So this, in a sense, shows how we can emulate a full RF channel for doing things like SatCom testing of transmit receive modules. We're using our VST for a full up and down link, so we have our duplex system doing the up and down links and the coprocessors to emulate that in real time in stream. So thanks for joining me today. For more information on chess, we do have an upcoming webinar. I encourage you to look out for information on chess and the other things it can do. Check out ni.com/chess. Thanks for joining me today, and look forward to seeing you soon.